the usual crowd, because yesterday we had another seminar, and usually morning crowds are much less. But he also need to leave later today, so we have scheduled this time. I'm very happy to introduce today's speaker, Dr. Tissa Illangasekare. He received his PhD in civil engineering from Colorado State University. And interesting enough, he has an honorary doctorate from Uppsala University in Sweden. He is currently the AMAX Distinguished Chair and Professor of Civil Engineering at the Colorado School of Mines, and the Director of the Center for Experimental Study for Subsurface Environmental Processes. He has been very active and had a distinguished career. Like in 2007, he was Hydrologic Science Program Director at NSF. He's a fellow of the American Geophysical Union, American Society of Civil Engineers, and the American Association for Advancement of Sciences. He won the WRRC medal from European Geoscience Union in 2012. He's the best editor of Water Resources Research in the AGU journal. He's also the best hydrology editor of Earth Science Review, and currently the co-editor of Value Zone Journal. That's true, right?
No, I think I was a past.
You was a past.
Done and all that stuff.
I see. Not much work. His expertise is in mathematical and numerical modeling of flow and transport on porous media and transfractured media. He worked also on unsaturated and saturated zone processes, surface and subsurface water interaction, snow hydrology, land atmospheric interaction, multi-phase flow, and this is something we shared many years ago when we shared that same interest. Also aquifer irrigation and many others, but the subject of his interest to him lately is scale processes, where you transfer lab measurements to field. And also recently, no, not recently, a few years ago, he led a group of scientists to visit Sri Lanka after the tsunami of 2004. I think you're going to touch on that today too. Okay, so without further ado, Tissa.
I don't think I need a speaker here, so because it's a small group. Hey, thank you for coming, and actually I'm not disappointed at all, because these are one of those things I asked to do it, and I keep changing the time because I have to catch a flight today. I was taken prisoner by my wife to see her eye yesterday, so I couldn't do it yesterday. So this morning I got up, actually I sort of did a mistake. I came out of the hotel and I saw everybody wearing this type of shirts, and I had a tie because I was coming from another meeting last Friday. And I thought, oh, I will debate let's put the tie or not. As soon as I came down, I know it's a big mistake because I saw everybody's wearing this type of shirt. As soon as I go back, I'm going to get a new shirt like this. I sort of, thanks for the introduction, and I think I had known him for a long time, and I feel so sorry that I have been involved in some conferences with him, and he asked me to come down here, but I never got the chance to come, and I'm glad I came. Hopefully he's not the last, so I'll come back and spend a little more time here. So I'm going to do a little bit of cheating today, because when I was asked to this talk together, I was thinking of, not sure exactly who is going to be here, so I thought I'd give a very general talk. But the general talk I'm going to give is actually a talk I gave. We mentioned that I got this medal last year, the Darcy medal, so they asked me to give a very general talk, inspirational talk sort of thing. So I decided to use the same slides, but I sort of modified it a little bit to make it more general, getting more specific into some areas I've been working on recently. So these are some of the slides I borrowed from that one. So I think one of the things you see, the point I was trying to make in this particular talk, in my Darcy medal talk, was the need for observing. So I was actually using the title, Let Us Keep Observing and Playing Now Sandboxes. So that's what I've been doing last several years. The argument is that actually, so when I was coming out this title, I went to Google and I got 11 million Google hits on playing in sandboxes. So I was surprised to see why it was. The reason for that is that sandboxes are really used by child psychologists and others to see how kids do things and behave. They have written many papers. So I was looking for a definition, and I found some interesting game called the sandbox. So basically the idea is that this campaign doesn't have any specific specified storyline, and you're free to wander and find adventure. So that is the way I tell my students when they come to work with me and say, okay, you have this difficult problem, why don't you do some experiments and see what happens, and then see how they can model it or not. So I think, so a lot of the things I do now is actually follow this type of thinking that before I write my equations, I try to understand what goes on, and you see some of those examples as I go, staying within this theme. So these are the type of sandboxes we play with. These are one of the, here a little bit. So these are the sandboxes we play. These are one of the big sandbox we use to actually look at some interesting problems of using a wireless sensor network for environmental monitoring. So this is we have a bunch of wells, and then we fill this sand, and then with all these sensors and transmitters. So these are a little more sophisticated sandboxes. But I think the point of this presentation is that you can actually learn a lot by looking at these problems experimentally. So you may say that we can learn this thing in the field, but I make an argument that when you are looking at very fundamental processes, some of the newer problems we are looking at, the fundamental physics can be understood much better under laboratory systems, but that cannot be done in little simple columns. It has to be done in multi-scale testing and modeling as the theme of this presentation. So this is an example of one of those sandboxes where we have we fill this sandbox with these are 28,000 cells. We know exact hydraulic conductivity. We have sensors. We have all sorts of devices to see what's happening inside this box. So these are really good test system for us to get a fundamental understanding of the processes, as well as use that understanding to put into models, and models then go to the field and do case studies in the field and see this thing works. So the theme of the presentation I gave for my Darcy talk is that we still believe that theory-driven experiment at various test scales can play a central role in providing answer to critical scientific questions, or they will help to fill knowledge gaps at this emerging problem in hydrology and water. So the general thinking has been that we go to the field as hydrologists, we try to understand everything in the field, which is true. Of course, we have to go to the field. But I think some of the emerging problems we are going to talk about requires us to actually go back into downscale these problems, to understand the process at a more fundamental scale, and see how that information can be used to solve this complex problem. So some of the problems I'm sort of talk about this our work I do now, like climate problems and the water for food, carbon storage, and there's some tsunami work I did, and some work we do in the arid region hydrology and this carbon sequestration and other areas now. So I think in this talk I was trying to give a little bit of history of the subject, but it was interesting that I had the whole collection of journals of WRRC from 1965. I inherited from one of my old friends who passed away. So I was looking at the first issue. In the first issue, these are the type of things we talked about in 1965, flood control, water movement. These are all the papers. There was one or two papers in groundwater. So then so if you look at the groundwater hydrology, the time maybe Ali and we were in grad school, this is the way groundwater hydrology looked like. We have the groundwater hydrologists here. I'm not saying that we are the center of the universe or anything like that, but these are the people we have to deal with. We have some people in soil physics, hydraulics, atmospheric science, geophysics. So these are all connected to the groundwater hydrology. This is the way the groundwater hydrology field goes. But I think you can see now actually, it doesn't have been the center, but as groundwater hydrologists, we also had to deal with all these interconnections. And I think there's a message which is going to come out at the end of my talk, that I think how we have to deal with this type of complicated problem, how do we deal with this problem using multidisciplinary approaches, that some of you are going to go into academia will realize that in the future, when you write proposals, it's almost impossible to get money writing a proposal based on what you're working on. You have to work with many other people looking at these interfaces of this problem. So I want to make a message at the end of the talk. So I'm going to go through this slide fast because we run out of time. So this is actually, I did the talk in 2012, and I was actually looking at some of the papers I was handling at that time, the editor. So you can see that from this traditional problem groundwater, we have gone to malaria, hydrochemicals, water evaporation, soil water dynamics. So you see how the field has changed. We in the WRR, when I finished my as editor, we get 1,500 papers a year, and I was sent about 300 to 400 papers in all these subjects which are so diverse compared to what we have been doing in the past. So the basic argument I'm making is that many majors in hydrology are open to experimental investigation still. There are experiments, very innovative experiments you can do to get understanding. And the improved understanding of the basic processes will help us develop models, and then it will continue to advance the household science. And then this is an important point actually, the theory-driven experiments. And when I was doing research for my Darcy medal talk, I did read a lot about Darcy, because when Darcy came out with Darcy's law, people always hear the story in 1832. He was a sanitary engineer. He was trying to develop a water filtering system. He put a column, put water on top of it, and showed that the velocity is proportional to the gradient of the head. But it's interesting to see that actually he had written many, many theoretical papers. So the Darcy actually knew the answer when he ran the experiment. So the whole point is that it was not an experiment. He discovered Darcy's law, but he discovered Darcy's law basic, looking at Navier-Stokes equation. He went back and looked at this, and he showed that if that is the case, this is going to work. So I think people sort of have forgotten Darcy that way. So I think that's the point I'm trying to make, is that it's not running experiments. It has to be experiment run on a well-developed theory. Then you know what question to be asked. So this is the type of research I do. So this is again a slide which may be interesting to students, that I think so most of the interesting problems are at the interfaces. This is some of you are working in these problems know very well. So I actually did my PhD work on river aquifer interaction. At that time, this was an exciting problem because the rivers move very fast, aquifers move very slow. When you try to couple these systems, the dynamics are complicated, and we didn't know how to do that, so we sort of developed it. Now look at this other problem we are dealing with now. So this is a problem I have been working on like unsaturated flow problem. Unsaturated flow problem, all the issues are how at this interface, or the capillarity effects. When you go into multi-phase flow, the dissolution of chemicals, I'm going to talk about CO2 dissolution, all these things happen at this interface. Now there are other interesting interfaces which we have to deal with, like land-atmospheric interface, and I'm going to talk about that later in climate change, evaporation, all these issues. These are very interesting interface. And this interface is very, very complicated because of the fact that the interface change, the land use change. And then another one is the land-ocean interface, and this is an example of the tsunami example I'm going to take. So the interfaces are challenging. I sort of mentioned these things. They are geometrically hard to define. If you look at the land-atmospheric interface, there's vegetation, there's rivers, all that. And the separate phase are abrupt transition. When you move from, if you look at the pore-scale, moving from the water to air, there's an abrupt transition. That transition happens through this interface. Similarly, you can argue the same thing about the interface between the saturated and the unsaturated zone. You can see, and the land-atmosphere is a really good example, and I'll show you some results later, that land-atmosphere interaction, you have Darcy's law in the soil, you have Navier-Stokes flow or Stokes law in the atmosphere. So there are energy and mass flux across these interfaces, and then there are contrasting flow and energy dynamics. Low velocities, high velocities, low Reynolds numbers, etc. And then these are very complicated to incorporate into numerical algorithms. So this is the approach we use. We go with multi-scale experimental testing, and I'm not going to talk about modeling. There's a parallel effort going on modeling. The idea here is that if you if you look at the most of the time as environmental engineers, when people scientists work in this column scale, they understand the biochemistry, chemistry, and biological process of flow, transport processes. But the real problem looks like this. There's a heterogeneities. There are, as you see in the site I work in Boise, Idaho, you see that this layered system, there are within these things we have heterogeneities. And then so as you go from this to here, there are two things happen. One is, can I get a glass of water? The dimension and anything water, so it doesn't have to be glass. So dimensionality changes, and then also the system becomes more heterogeneous as you go from here to here. So the complexity of this system comes from that. So just to give an example, if you take a column and you understand a biological process, we do this all the time in our remediation research, we get a 99% efficiency. I published a paper some time ago, we show into the field, we get a we get in the laboratory, I can get 90% efficiency of cleanup, and you go to the field, it goes to 23, 24%. Because of this issue, the heterogeneity and the dimensionality. Like if you have a microbial process going on this column, if I put water through this, the water is going to, the film growth, the water is stop moving. But in the field, when there's a microbial growth, the water is going to bypass. So these type of issues have to do with dimensionality. So these are one of my labs. I have 2 labs, and the one lab I have, where we have this large-scale physical model, different sizes. You see some of these pictures as you go, like a bird, fisheye view of. So the argument we use in this type of work is that so when you do experiment, the most important thing, as modelers we know, most important thing in model are the initial and boundary conditions. In the field, it's very difficult to control these things, very difficult to measure these things. So we make the argument that in the laboratory we can do this. Second one, in the field, you'll never get the heterogeneity. You cannot put enough holes in the ground to understand everything in the system. So anything you do in the field, if you drill a hole there, it is some sort of averaging between these two things. So you always miss the physics of what happens in this place. And the third one is the unit. If you are looking at theories, validation theories, this is an issue I had to deal with all the time in WRR when we get papers. The people do case studies, so we don't accept a lot of case studies in WRR for that reason that case studies doesn't allow. Case studies help you to understand that system, but it's very difficult to transfer that knowledge to another site unless you understand the fundamentals. So in these type of things, model validation, theory validation, we believe that can be done at the scales, type of scale we are looking at. These are very large physical models. So I'm going to take 3 examples, one on mass transfer, evaporation, and coastal aquifers. So these are the 3 problems I'm going to talk about using this approach. How can we control real-world problems if you understand the fundamental physics? So these examples are going to use how good science questions can be raised, and then how the scientific challenges have to overcome to provide answer to practical problem solution, then how to develop theoretical foundation, how to design good experiments, how observations are made to get new insight, and then how do you use this to make prediction and practical problem solution. So these are the 2 problems which have to do with multi-phase flow. These are in the interface we talked about in the pore-scale, where there's a mass and energy transfer across these interfaces. So one of the first problem is this, what are called dense non-aqueous phase liquids. These are solvents, petroleum waste, get in the ground, they get pooled and go like this, water goes through, and they pick up mass, and then you put in a well. And the second one we are working on a lot these days is this whole issue of carbon sequestration, where we inject the supercritical CO2 into deformation with the expectation that they are going to stay there for a long time. It's called permanence of storage. So these has to do with climate change. So these are some of the work some of my students, one of my former students, a professor at Louisiana State did it. So he actually looked at the very pore-scale. So in the pore-scale, these are the interfaces we talked about, the pore-scale. So these are 2 examples. These are hydrophobic grains, this is wetting grains, these are sand grains. You see this is a blob of napple inside the soil pore. And then what happens when the water flows, it's going to be mass transfer, it's going to be dissolution. Okay, so let's see what happens at the pore-scale. So these are interface I showed you in the example in the Boise site, where you have this sharp interface. So this is a fine sand layer, and this is a coarse sand layer. So if you have a non-wetting fluid, the chemical spilling, you see it comes down, and as it come down here at the pore-scale, due to this particular entry pressure effects, this napple doesn't go through and start pooling. Okay. So what is the implication of this? So in the real world, so these are some lab experiments. So we never understand this in the field because it's almost impossible to go to a site and understand how this thing is distributed. So we created this in our laboratory. These are 3 examples where we have a spill, and then we see how big it is spill. These are 2 examples where the D-napple spill here, it end up in this complex architecture. So they are unstable fingering. So the question we are asking is that these interfaces control this behavior of the chemical, but ultimately our goal is that if you pass water through this system, how this is going to appear as a breakthrough curve downstream. So again, to make my argument that these type of problems have to be built on a good theoretical foundation, so we look at how do we look at these problems. If a water goes through this, it's going to dissolve, and how do we model that? So we went to the literature and we found there's a, oh thank you, I'm sorry, I thought you didn't have to go there. I thought there's a little toilet here. Thank you. was not drinking or anything last time. That's good, thank you. So what we do here is that, so this is chemical engineers know this. What they do is they look at a dissolution of a plate. So we found that there's a relationship between, so ultimately the mass which is going to produce downstream depend on what you call mass transfer rate coefficient. You know, how much mass is going to come out of this dissolve from these entrapped sources. So then we also, so we can actually solve these equations and suppose some solution to this. You can get an equation which relate the what you call Sherwood number. This is a dimensionless mass transfer coefficient, which is related to Reynolds number, which has to do with inertial forces or the viscous force, and Schmidt number, which is also another dimensionless number using diffusion. So what we did was, this is some work I did when I was a sabbatic at Stanford. So I had a very smart student, and so I asked her to, so why don't you develop a COMSOL model to see whether, so this is the equation we got, see whether we can get a similar equation. So this thing came in a Journal of Hydrology paper recently, a few months ago. So what she did was she took this pore-scale model and then put an apple in here, pass the water through for different Peclet numbers, and in this case Reynolds number, Schmidt number, and then she came out with an equation very similar to what we had, except you see the difference is that these numbers are different, but they have the same functional form and they're very nice fit. So the point is that even though the complex process of mass transfer happened at larger scale, at a fundamental pore-scale, the process can be modeled using the physics or Navier law equation and things we know at a very fundamental level. So you can see these issues are very similar. So then the idea, we did this work a long time ago. This was to validate at the pore-scale. So we actually find a closed form solution to this problem. We are looking at a dissolution of a pipe. So this is very similar to the dissolution on Naples. Like some of you are familiar with these new problems in carbon sequestration. This is exactly what happens when you put CO2 into the ground. They behave like an apple, non-aqueous liquid, and the water goes to it to dissolve. Well, the idea is that dissolved mass is going to somehow mineralize, and then their long-term trapping. So you see this is a closed-form solution to this problem, and then you get a solution. One of my PhD students, Saba, probably you recognize him from Egypt. So that student did his PhD work with me, and we had to develop this model, and we found that we can get a relation very similar to this one. And the important thing is you see there's a length. So in this one, the solution depends on the length of the tube. Here we have some L star is some sort of effective length. So we actually did some lab experiments where we actually created this entrapment zone where we took a random field, and then we actually passed water through that. And then so our goal was to see whether if I know where this stuff is, this soil Naples is tough, whether I can predict the mass transfer rate coefficient. So we actually try to force this equation into this model. So we ran this again, going back to our experiments. So we understood that we have a good theory. We showed that the theory can be explained using the fundamental chemical engineering principles of mass transfer, transport, dispersion, diffusion, and then we actually ran a very complex experiment in our lab. We have this very large tank, and we filled with this random field, like 29,000 cells, and then we have a spill here. So we actually created the heterogeneity in the lab because we want to see how this system behaves in a high heterogeneity and low heterogeneity field. So we use these geostatistical methods. We get the same mean, but we use the different variances here. The larger the variance is more heterogeneous, it's a more homogeneous system. So what we again, these are publishing papers. I just want to make the point that so the idea here is to see whether we can get a upscale mass transfer rate coefficient. So what we found was that if you don't upscale, in this case we ran an experiment, we had observed the flux versus model prediction. If you don't upscale, they don't match. But we came up with upscaling theory where we showed that the effective mass transfer rate coefficient depends on the statistics of your the subsurface system as well as the architecture. In this particular case, the moments. And again, these are details. I just want to make the point here that you can develop this upscaling method where the fundamental physics is built into this equation. At the same time, you can capture the information of the field system using the geostatistical method. So we are trying to use the same ideas in our carbon sequestration problem. I think so these are some of the early papers we did on this upscaling. So the second problem I wanted to talk about is this land-atmospheric interaction. This is a very complicated interface, like I mentioned, because the fact that all this heat, mass flux happens at this interface, and then you have these trees growing. So we define this shallow subsurface to be some like a 200 centimeter depth below the ground surface. So this is shallow enough, it is not affected too much by the water table. But there are problems, these are the problems we are working on now. We are looking at the land-atmospheric interaction in evaporation in climate models. I'm going to talk a little more details. And the chemical vapor intrusion. This is a very important problem. Actually, a lot of the sites in USA, waste sites, they closed these sites many years ago, but now they are finding that even the sites are closed, when in the buildings, the cracks in the walls in your basement, the vapor can come into the building, and the average American spends something like 20 some hours inside buildings, and then so if you breathe this for a long time, they really don't know what the long-term implications of this. And this problem, we hypothesize that the way the vapor gets into the building is controlled by the dynamics of what's happening in the radar zone. And again, I'm not going to talk about this. Another one, we are working on landmine detection. These are all landmines in the interface here, and the frozen soil, permafrost. So I'm going to I'm going to talk about soil-borne evaporation climate modeling, and this is a reference, which is the point I'm trying to make. The land surface is a critical interface through which climate change impacts humans and ecosystem, and through which humans and ecosystem can affect global environmental change. So even though the land surface, like we talked about, is happening at a very, very micro scale, all the mass and heat flux happens at that interface. So this has main implications on climate model. So we are doing a lot of research to understand how these processes get upscaled into climate models. So we'll talk about that. Again, these are some slides I have borrowed from others, and you understand that read through this. So global evaporation is a very, very important part of the global hydrologic cycle. If you look at the literature, actually we know very little about how these things happen from physics point of view, because a lot of the atmospheric scientists just assume this like a black box. They just look at the surface, they assume evaporation, and then they put it in their model. So we are actually looking at this more carefully to see whether what are the implications of this type of assumption on climate model prediction. Just to make the point, I have been sort of using these slides in many talks. So if you look at the climate models, you are looking at kilometer-sized block cells, hundreds of meters, and then you go to vertical direction, they are kilometer scale. Now we try to couple this atmospheric model to soil model, and now we are talking about centimeters. The question we are asking is that things like, people do this type of model, develop models and say that, okay, I'm going to use Richard's equation, I'm going to run Venusian parameters, these type of things at this scale, and these type of parameters exist in this 1,000-meter scales. So they force the models to take these parameters, doesn't make any physical sense, but they don't know what to do. So we are questioning these things and say, okay, if you don't understand the physics at this smaller scale, everything you at the larger scale will have problems. So this is a hard sell for us, for the atmospheric scientists, because they say that there are no way we're going to characterize this system to scale. You guys want us to do it, but it cannot be done. So these are valid points. At least what we believe is that if you understand the physics, then we can look at what are the effective parameters which are measured at the larger scale, then we can actually at least improve this climate models. So we are focusing what are called community land models. So we're just starting a project at Berkeley. So we are having a proposal like to look at this. How can you improve this model? So if you look at this climate model, there are various levels of climate model, individual vegetation, but this is what we are interested in, seeing what happens at these interfaces where all these things are happening. So the challenge is that now I've been preaching that, okay, these type of problems have been studied in the field. So this is not easy. So that requires us to be really innovative to do this. So what we did was, okay, I'll talk about it later, but I want to make a point here that now with atmospheric scientists, what they do is they treat the soil to be evaporation is a one big leaf. Or evaporation from bare soils is this E, which is controlled by what is happening in the soil, what is happening in the atmosphere. But actually they never look at what happens here. Sometimes when you have evaporation, this thing completely goes dry. When it goes dry, the mechanism by which the water is going to go into by diffusion, and there are no water at all, it's just gas. So then you go and define the soil moisture, and the soil moisture doesn't mean anything here, because there are no soil moisture here, soil moisture is down somewhere here. So these become real problems in modeling. What the climate modelers do is they actually say that they don't know how to get the soil moisture, so they actually use models to predict soil moisture. So in a way, some of you are working in surface-subsurface interaction, we know the capillary fringe is so important, but here they are saying that the interface is so important, but the model itself calculated these things which goes back into the model. So this has a lot of interesting implications because we are making this climate prediction based on a physics which is not captured in these models at that scale. So the grand challenge for this type of problems is how do I